Okay, thanks everyone. Welcome back for the final talk of today, but not the final event of the conference for today. We'll have Doreen Fraser, who will be presenting a talk, Why Can We Use Analytic Continuation to Relate Relativistic QFT Models to Non-Relativistic Models? And immediately following her talk, we'll have a discussion between all three of the speakers from today, along with you, the audience, and I'll be moderating that discussion. So without further ado, Doreen.
Thank you, Mike, and thank you to everybody for coming to this conference. I'm really excited about how it started out and looking forward to the discussions over the next couple of days. So the talk, I'm going to pick up in certain ways on certain themes from the last talk, but from a completely different angle. So the question I've posed to myself is the question of why we can use analytic continuation to relate relativistic quantum field theory models to non-relativistic models. So before I dive into it, I wanted to set a little bit of the context for you and give you some motivation for why I'm interested in this topic. To give you a bit of background, I'm sure anybody who has studied any quantum field theory in any capacity is familiar with the Wick rotation, which is a rotation which rotates t time to negative imaginary time. And the effect it has is to transform in relativistic quantum field theory. You have Lorentz invariant for vector products. And the effect it has is to transform those into negative Euclidean for vector products. So immediately we then leap to thinking about why we have Minkowski space in quantum field theory in the first place. And of course, we had Minkowski space and Lorentz symmetries, which are related to Poincare transformations. Oh, that's the right one. Okay, Poincare transformations. And so we are familiar with that structure on the space-time structure on the Minkowski side. On the other side, we have Euclidean transformations that come along with these products. So we get translations, rotations, and reflections. All right, so here is my motivation for being interested in this question in the first place. So one thing I've been thinking about lately is the relationship between a whole bunch of models that we find in condensed matter physics on the one side and a whole bunch of models we find in particle physics and relativistic QFT on the other side. And if you look at the history of 20th century physics, one of the themes is that a fruitful way to proceed in physics, if you don't know what to do next, is to, if you're working in QFT, to look at condensed matter physics, a condensed matter physics model for inspiration, try to pick up an idea, and then use it to solve some problem that you can't solve in quantum field theory. And it goes in both directions. The importance of the connections. So thinking about this philosophically in terms of what kind of reasoning is involved in this move, analogies between our condensed matter physics systems and our particle physics systems play an important role. My thesis that I've been defending in a bunch of works lately is that if you look carefully at these analogies, you can appreciate that the analogies that play an important role are purely formal analogies. So what I mean by that is what we're doing is we latch on to a mathematical structure on one side, say the condensed matter side, and then we lift that mathematical structure that we're interested in up, and we apply it again on the QFT side. So another alternative would be that the analogies are physical analogies, which would mean that there's some physical justification or some physical similarity that we're latching onto when we make these analogical reasoning moves. So I think that's actually not the case in these quantum theory examples, and that's what I think makes them interesting in the history of physics. So one objection that I've encountered in giving talks on this topic is the following. So sure, I talk a lot about how in the condensed matter physics side, often what we have are non-relativistic models. And so then when we're thinking about how they correspond to the models we're interested in on the quantum field theory side, which are space-time models, often you end up mapping space to time somehow. Right? So clearly that's going to undermine a lot of the physical interpretation that you're trying to take from one side to the other. The possible objection I've encountered here, though, is you need to look at what's happening. Often when we're making these mappings and we're doing these analogies, we're invoking a Wick rotation. We're analytically continuing one model to the other model. And this is where you're going to find, when you look carefully at this analytic continuation, is that that's going to be where you find there's physical facts coming in. So if you ask why we can analytically continue in this way, you're going to be appealing to the physics. Therefore, there's some physical basis for these analogies. Therefore, they're not formal as I'm claiming. Okay, so my main motivation here is I've been pressed to think about this a little bit more, so I'm going to respond to the objection. So you're not going to be surprised. I'm going to give away my conclusion. So my conclusion is going to be, actually, no, the physical facts are not explaining why we can Wick rotate or make this analytical continuation move. All right, so that's the motivation and the context. So here's an overview of what I'm going to do during my time. So first of all, this is of course a philosophical talk, so the first thing I have to do is I have to sharpen the question I'm going to ask and talk a little bit about kinds of explanations that we can offer. Then I'm going to first think about what Wick rotation or analytic continuation looks like in the perturbative context in which it initially came up in quantum electrodynamics. So I'm going to go all the way back to Dyson in 1949. Then I'm going to shift to looking at analytic continuation as a strategy in non-perturbative approaches to quantum field theory. I have a lot more to say about this, but to situate it for you right now, Szymanczyk was the one who really started this off. Kenneth Wilson, who is best known for renormalization group methods, but also worked on lattice QCD, was also engaged in thinking about this. And then in the more axiomatic tradition, you have constructive field theorists who use Euclidean approaches to construct field theories. Then I'm going to conclude with conclusions. All right, so the question I posed in my title was the question of why we can use analytic continuation to relate relativistic quantum field theory models on the one hand to non-relativistic models on the other hand. So to restate the question in slightly sharper form, what I'm interested in answering is the question of why we're able to successfully apply this mathematical technique of analytic continuation in the context of quantum field theory. So I did mention it goes in both directions. I'm primarily interested in what it does for us in the context of quantum field theory and how it serves us there. Okay, so I'm going to put up at the beginning here two candidate explanations for why we can analytically continue. So they are going to contrast with one another. The first one is the explanation that I will be calling explanation one, the mathematical trick explanation. So why are we able to successfully apply analytic continuation? Well, what we're doing is we're changing variables, and we're changing variables in a way that reposes our original mathematical problem in a form that makes it mathematically more tractable. So I think a comparable example that I have in my head when I'm thinking about this is if you think about in the physical context of, say, general relativity, an important issue that we have to think about is singularities in metrics. So, for example, back in the very early history of general relativity, there were questions about the Schwarzschild metric and whether the Schwarzschild radius was there was a singularity at that point in the original coordinates that were chosen, so there was the question about whether it was a genuine space-time singularity or what was going on. It was later, I think, it's now understood that that's merely an effect of choosing a particular set of coordinates. And so choose a different set of coordinates if you don't want to have everything blowing up for you in your representation in that place. So I think this sort of explanation for why we analytically continue is an explanation which appeals to the fact that we want to get rid of singularities that are standing in our way if we want to calculate certain types of quantities. So we do a coordinate transformation. The important thing about this explanation for me is it doesn't tell us anything interesting about the underlying physics. It doesn't tell us nothing about the underlying physics, but it doesn't tell us anything interesting about the underlying physics. So that's candidate number one. Candidate number two is an explanation which does appeal to the physics to explain why we can analytically continue. So this is the sort of objection that I mentioned I'd heard in some form that I'm trying to kind of reconstruct here. So the idea here goes back to the physical symmetries I had on the first slide that come from doing the analytic continuation move from the Lorentz symmetries to the Euclidean ones. So the idea here is that the successful application of this technique is explained by the fact that our change of variables is taking the Minkowski space structure and it's mapping it to Euclidean space structure. Aha! A characteristic physical property of special relativistic theories, such as quantum field theory, is this Minkowski space-time structure. So this must be what explains the success of this mathematical technique. So I see some people going, what are you talking about? Okay, so I think, yes, this version might seem puzzling because, well, wait, a Minkowski space-time structure does encode important physical characteristics that we want to have in our quantum field theory, but we think that Euclidean space structure doesn't do that, right? So if this is supposed to be really important for our theory, seems like something is going amiss here. And so I think this is the intuition you can find if you look at, I'm going to be coming back to Schwinger in a few minutes, but if you look at Schwinger's reflections on this question of using Euclidean formulations of quantum field theory. So in this paper in 1958 on the Euclidean structure of relativistic field theory, he says, the nature of physical experience is largely conditioned by the topology of space-time with its indefinite Lorentz metric. It's somewhat remarkable then to find that a detailed correspondence can be established between relativistic quantum field theory and a mathematical image based on a four-dimensional Euclidean manifold. Right, this is where the puzzling response to that comes in. The objects that convey this correspondence are the Green's functions of quantum field theory, which contain all possible physical information. The Green's functions can be defined as vacuum state expectation values of time-ordered field products. So we're going to come back to these vacuum expectation values in a few minutes. But here, he thinks that this is not an explanation. In fact, this might be something you find puzzling, so it would be surprising, which would be the opposite of an explanation, right? The opposite of a good reason why something is the case. I'm going to push a little bit further because I want to have these two options on the table. So here's my attempt to at least make this precise enough for the purposes of my talk and what I want to get into. So really, analytic continuation maps our Minkowskian structure to a Euclidean structure that's somehow structurally equivalent to the original one we were looking at, in the sense that it's going to encode the relevant physical content of our quantum field theory. So I think that this is the sort of core of this explanation, which looks to the physical symmetries to be giving you the reason why analytic continuation is working. At the same time, though, so here I have my two candidate explanations. So on the one hand, you have the sort of deflationary one that it's a sort of mathematical trick that we can explain away. The second one is appealing to some sort of physical basis for being able to make this move. So I still think, so I think that there's evidence in the literature that people go back and forth on this question of what's really going on in this case. which I think is natural. I think, so here's another quote from Schwinger, which I hope will tie into some of the talks we're going to have tomorrow. So this is him reflecting on the feedback he got to this 1958 paper in which he was thinking about what these Euclidean theories that you get from analytically continuing from your QFTs look like. I well recall the reception this received, running the gamut from it's wrong to it's trivial. So in my terms here, I think it's trivial means, of course, you can analytically continue to a Euclidean theory. It's a nice mathematical trick where we change our variables, and that's trivial. To it's wrong. And I think this is the it's wrong intuition, which is coming from maybe the quote from the beginning of Schwinger, where it's wrong because you need to have some sort of physical explanation for why we can do this, make this mathematical move. And so that's in terms of physical symmetries. And so you think a Euclidean theory just can't give you special relativistic physics. Okay, so this is just an example of how people can go back and forth. All right, so now I'm moving on to part 2, where I look at the perturbative quantum electrodynamics. So I take it that this is a fairly straightforward case. That's a nice kind of warm-up case. So my conclusion here is, number 1, mathematical trick is definitely the way to go. So Dyson in 1949 has this paper called the S matrix in quantum electrodynamics. And the aim of his paper is to show that if you apply Feynman diagram techniques to S matrix elements, then you can use them to take care of all the ultraviolet divergences to any finite order and perturbation theory. So in the context of making the case for this, he makes a move he's working in energy rather than time. Energy goes to negative imaginary energy in his variables of integration. And he gives a clear justification for this move, which is that the change of variables is legitimate because the function's analytic at the relevant values. So it's a legitimate mathematical move. How does this help? Well, it helps because what he's doing here is he's moving the paths of integration away from the mass shell singularities that he had in the original propagator. In terms of the denominators that he's working with in his formulas, the indefinite Minkowski products are replaced by the negative definite Euclidean products, and so he can get finite answers where before he was getting infinite answers, before there were divergences. Okay, so I think this is a clear case in which he is employing a change of variables, which is a useful mathematical trick to calculate what he wants to calculate. Following the sort of historical path, an important development in thinking about Euclidean theories as counterparts to relativistic quantum field theories was this paper by Schwinger that I mentioned a moment ago. And what he was really interested in doing was thinking about what happens and how you would characterize the set of correlation functions that you get. If you start with the vacuum expectation values from your quantum field theory, so that would be, so I have the E's are Euclidean. So this is after you've made the Wick rotation or the analytic continuation move. But so you have this set of vacuum expectation values. And so we have the term Schwinger function that's still used in the literature. And that refers to these functions which are just obtained by taking a set of vacuum expectation values from your QFT and then doing the Wick rotation move. So he pointed out that in the context of Lagrangian field theories, if you do this, then the Schwinger functions are going to satisfy equations that are invariant under the inhomogeneous SO4 group. So he was trying to figure out what the theory looks like that has these as correlation functions. And so he was looking at the Euclidean properties of this theory. Okay, so that's going a bit farther than Dyson did. The next step is to turn this into a kind of strategy. So there's a paper by Szymanczyk from 1966, which turned out to be actually very influential in physics, which he published in the Journal of Mathematical Physics, Euclidean quantum field theory. And the idea he was advocating in this paper is that we should adopt a Euclidean strategy for constructing models of quantum field theory. So the idea here was that we should adopt this kind of two-step process. So forget about starting with a set of vacuum expectation values from a quantum field theory. We're going to start with Euclidean theory. So he says, look, formulate some Euclidean theory, theory X, in some manner, it doesn't matter, which is going to generate for you a set of Schwinger functions as its expectation values. And then we should analytically continue back from our Euclidean theory X to get a quantum field theory. So this was a strategy that is a way of getting a quantum field theory model that's different from canonical quantization, right? So comparing to Dyson, this is a strategy that's a non-perturbative strategy. I mean, you could use perturbation theory if you want, but he's not just focusing on perturbation theory within quantum field theory when he's applying his analytic continuation move. And he is building on Schwinger's contribution by suggesting that we should take our Euclidean theory and then analytically continue back to get the quantum field theory, which is the thing we really care about in this context. Okay, so this was a suggestion which was initially ignored, but then became, within 5 or so years, an important piece of, important idea that was taken up by a number of people. So on the left here, we have Ken Wilson, who is best known for renormalization group methods. And so in his papers in which he is developing renormalization group methods, and his Nobel Prize lecture where he describes what his motivations were, he points to this paper by Szymanczyk as giving him this clue that what he needed to do was introduce this Wick rotation, the analytic continuation move, and think about Euclidean field theories. On the other hand, on the other side here, you have, in the more mathematical physics tradition, you have constructive field theorists. This is a picture of Barry Simon. You have constructive field theorists who pick up on the same idea and think about the Euclidean strategy as a method for constructing models for axioms, axiomatic systems for quantum field theory in a more mathematically rigorous way. Okay, so I'm going to follow up on this side of the picture, but I think it's important to realize that there's intersection in motives and in the history here. Okay, so this is the point at which I get to thinking about how things look when we shift to thinking about QFT non-perturbatively. So what I have here is a quote from Strokey's book, which is an introduction to non-perturbative foundations of quantum field theory. This is a nice quote. Essentially what I'm going to do is I agree with his assessment here. I'm just going to unpack what he says for the purposes of this talk. So here's what he says. He says, to set this up, we're going to be thinking about the Whiteman axioms for quantum field theory, which are going to be really useful for us because in contrast, one reason they're going to be useful is because in contrast to the algebraic axioms for QFT, they're much more permissive about the analyticity properties that you have for your functions, right? And this is going to be important to the story as it goes on here. The other reason why this is the relevant framework to be thinking about here is because the Whiteman functions are vacuum expectation values. So you analytically continue those to get the Schwinger functions. So that's a natural place in which to be thinking about the analytic continuation move. Okay, so the analyticity properties of the Whiteman functions provide the mathematical basis of the heuristic prescription of defining the Euclidean field theory by replacing T by IT. In particular, it guarantees that such a transformation does not connect disjoint regions of analyticity, for example, separated by cuts of non-analyticity, which would make the relation with the real-time theory rather loose, if not void. Moreover, the heuristic prescription misses the role of the spectral condition, covariance, locality, and the need of excluding coincident points. Okay, here's the important part for right now. Such a deep structural relation is one of the rewarding results of the analysis of the general properties of the vacuum expectation values. Okay, one of the reasons why he's writing this whole book on the topic. Okay, so what is he trying to explain here in this quote? Well, what he wants to explain is why we can take the Whiteman functions, which are the vacuum expectation values, and analytically continue them to Schwinger functions, and then the non-coincident points he's telling us is a very important point here, right? So we can at least analytically continue them to Schwinger functions on all of our non-coincident Euclidean points. Okay, so the other piece of the puzzle in the background is that when he talks about the Euclidean field theory, he has in mind a particular example of a Euclidean field theory, and that is the one you get in the context of the Oster-Walder-Schrader reconstruction theorem. And what is that? That is, so there's a set of axioms, and the reconstruction theorem proves that those axioms are sufficient conditions on a set of Schwinger functions for constructing a model of quantum field theory that satisfies the Whiteman axioms. All right, so I will get there, but I'm going to do it in steps. So, okay. So first step is to back up and to think about the Whiteman reconstruction theorem. So the Whiteman reconstruction theory. So here we have we're entirely within quantum field theory here. We're not doing any Wick rotation, no analytic continuation moves yet. That is the next step. Okay, so the Whiteman axioms are a set of physical principles which mathematically encode what we expect a quantum field theory should look like, i.e. they are axioms which contain quantum theoretic assumptions, principles, and special relativistic ones. The details are not important for our purposes. Some of these ones are similar to ones that already came up in the last talk. So this is our goal. What we want is we would like a model of the Whiteman axioms. And so what do we need to do that? We need a Hilbert space. We need a set of fields. We're going to smear them with a set of test functions. We need a vacuum, and U is going to be the implementation of the Poincaré group of symmetries that we care about in our relativistic field theory. Okay, so how do we get there is the question. The hard part is trying to construct a model that has all of these features. So what we're going to do is we're going to get there somewhat indirectly by backing up a step and considering a set of vacuum expectation values. And the set of vacuum expectation values so what we want to do is we want to find a set of vacuum expectation values that we can use to construct the full theory that has all of these nice physical features that we care about. And so how does that work? Well, within the Whiteman framework, what Whiteman showed with his reconstruction theorem is that if you impose a set of properties on the Whiteman functions, then you can reconstruct the full model of his QFT axioms. Okay, so what are these assumptions? Well, they're properties of the Whiteman functions. So this is where some of these are going to be properties that are going to be giving us rather directly some of these analyticity properties that we care about, right? So the details of what these are is not, I think, important for the logic of my talk, but you can see that because we're sort of reverse engineering this situation, so we know what we want is this, so we're going to we're going to impose at this lower level on the vacuum expectation values mathematical properties that then are going to allow us to get the physical properties that we want. So these two sets of properties are related closely, but these ones are applied to the vacuum expectation values. Okay, so here's where we get to analyticity, which is what we need in order to understand that strokey quote I had on the slide a minute ago. Okay, so what you can show is so now we're at the level of assumptions that we've made about properties that our vacuum expectation values have to have. So if you take 3 of these assumptions, so one of them is our covariance assumption, Lorentz covariance assumption. There's a local commutativity assumption, which we heard about in the previous talk. This is a version of that just applied to the vacuum expectation values. And then you have a spectral condition, which came up already as well, applied to the vacuum expectation values. And so these 3 assumptions are going to guarantee that our Whiteman functions can be analytically continued to our entire set of non-coincident Euclidean points. So essentially what we're doing here is these assumptions are telling us that our Whiteman functions are analytic in the domain that we care about, right? So, all right, so let's revisit this quote then and unpack what his explanation is for the usefulness of this heuristic prescription, as he puts it, of the analytic continuation or the Wick rotation move. Okay, so again, I think it's important not to lose sight of what people are trying to explain. So what he's explaining is why it's mathematically possible to analytically continue in a non-trivial manner. So the non-triviality is what's secured by the previous slide here. So it's important for us that we can analytically continue our Whiteman functions on this entire set of non-coincident Euclidean points. So this is the domain that we're interested in, so that is important. So compare here, I think, what he's trying to explain to what Dyson is trying to explain, and the sort of type of explanation that Dyson gives is very similar. So Dyson says, look, this is a legitimate change of variables for me because the function that I'm dealing with is analytic on these points at which I'm applying this Wick rotation. Actually, later it was called a Wick rotation. Wick hadn't done his work on it yet, so then it was just analytic continuation. All right, so the explanation that Strokey is giving here is also similar to Dyson's in that the motivation for analytically continuing is also related to singularities that are coming up in this context. So so after he talks about the result, Strokey gives some sort of little toy model examples, comparing the Euclidean model and the singularities that come up in it with the full relativistic model. And so even for very simple, like 2-point expectation values for scalar theories, you get on the relativistic side, you have singularities across all the light cones and on a bunch of other cones as well. But then once you analytically continue, you have a singularity at the origin. So it really does help you in the sense that it gets rid of singularities that are a pain to deal with. Okay, so all right, so so the upshot I think here is that looking at the second part first, there's mathematical conditions on the Whiteman functions that ensure that the functions are analytic and thus that it's mathematically possible to apply the mathematical trick of analytic continuation, which is similar to what Dyson says. What is different from what Dyson says, though, is that these mathematical conditions that we applied on the set of Whiteman on the set of Whiteman functions is physically motivated. Okay, so what the important assumptions are the spectral condition and covariance and locality. So clearly, those are physically motivated assumptions. Okay, but I do want to argue, so now some physics is coming in, but I still want to maintain that he's not giving an explanation in the mode of what I've called explanation 2, the physical symmetry type of explanation. So he is appealing to these physically motivated mathematical requirements on the Whiteman functions. But the reason he's doing that is to secure the analyticity of the functions on the domain that he cares about. And he's not, and what doesn't come into it is, I think, the second part of what I have here, right? So he's not appealing to anything to do with a structural correspondence between the Euclidean theory and the quantum field theory. So what I mean there is, we go back to the previous slide. He is appealing to these physical conditions, but the reason he's doing that is to establish that the functions are appropriately analytic. He's not saying anything about what the properties of the Euclidean theory are at this point. Right? He doesn't even talk about that. This is all about the properties that the Whiteman theory has. All right. So as an aside, I started out trying to reconstruct this objection by just looking at the Minkowski, the Poincaré covariance and comparing that to the Euclidean covariance that we have on the Euclidean side. And thinking that the symmetries were encoding the important structure. You already see here that we're going well beyond that because covariance is only one of the assumptions that's coming up here, right? So now there's a lot more physical structure beyond just the requirement of Lorentz covariance that's coming into this argument. Okay, but that's not the main point I wanted to make. Okay. So here's the segue to the part where the properties of the Euclidean structure do come in an important way. That is when you get to the project of reconstructing the quantum field theory on the Euclidean side. To orient you, this is just what I had before. So this is all in QFT. This is the Whiteman, our model of the Whiteman axioms, and this is the set of vacuum expectation values that satisfies the Whiteman properties on our and then we can use to reconstruct that. The Euclidean stuff is all over here. Okay, so recall that the motivation for this reconstruction theorem is an attempt to realize the semantics idea that a way we can get at this thing we care about, this model of quantum field theory, is to start with a Euclidean theory. The problem that they posed is, of course, we know we can go this direction, right? That's well established. Cut this off. Forget about this part here. Can we start here with this square in the bottom left? And if we have a set of Schwinger functions, doesn't matter how we've obtained them. Could be some sort of functional integration strategy. It could be a lattice regularization we've used from some other model. However you get this set of Schwinger functions, the question is, under what circumstances can we take this set of Schwinger functions and then reconstruct our quantum field theory model that satisfies the Whiteman axioms? Okay, so on this side, and this is going to be a very short version of the story, on this side, what Osterwalder and Schrader established is that, yes, there is a set of properties that you can require that this set of Schwinger functions satisfies. If they satisfy that set of properties, then you can reconstruct and get everything you need for this model of Whiteman quantum field theory that we're trying to get at. And so essentially what they do is they're not starting from scratch. Up here, they proceed by copying all the moves that are made in the Whiteman reconstruction theorem. And so they figure out what properties they need to have over here so that they can just copy all these moves and construct everything that in an analogous manner to what you get over here. So what this looks like is how you construct your Hilbert space. To give you an idea, is you start with your Schwinger functions, you get a set of, Euclidean spaces over here. So these are your you get a set of Euclidean fields, which are a abelian algebra of Euclidean fields. And you have to the tricky part's figuring out what the functions are supposed to be, figure out what those are that satisfy the right conditions. There's a vacuum state. And then that's how you construct your Hilbert space. And then you identify the vectors in the Hilbert space with what you have over here. So over here is the set of Whiteman functions, Whiteman field operators that satisfy the Whiteman axioms. Okay, so the upshot of this is that you can construct as Szymanczyk envisioned. You can use this strategy to construct a model of the Whiteman axioms by mimicking what you've already got on the other side. Okay, so back to my question. So this is starting to look closer to explanation 2, in the sense that what we've got in this case is we've got a Euclidean theory, the set of Schwinger functions that satisfy the set of Schwinger properties, and then we have these Euclidean fields and vacuum states and all of that. And we've got our QFT, and the whole project works by making sure that our Euclidean field theory encodes all the physical structure we care about on the QFT side, right? Because all we're doing is mimicking the strategy that was used by Whiteman to reconstruct his theory from the vacuum expectation values. Okay, so you do have an encoding of the physical content in the way that I wanted here, but this is due to a sort of reverse engineering of the Euclidean theory for the purposes of constructing our Whiteman QFT model. So we've chosen the Osterwalder-Schrader axioms because they're counterparts of the Whiteman properties. So this is the sort of mode of explanation which then I think would support an appeal to there being a physical explanation that appeals to not just the symmetries, but a lot of the deeper structure of the quantum field theory. So I think this is an explanation of why we can construct a Whiteman QFT model using this Euclidean strategy and why that succeeds. But of course, we always have to be paying attention to what kind of thing what we're explaining here. So I think that's a fair explanation of why this reconstruction strategy works, but it doesn't explain the original, it's not an answer to the original question I posed, right? So the original question I posed was about the why analytic continuation works. I already gave you that explanation when we went way back. If you go way back here, so I already gave you that explanation from the Strokey side, and that didn't involve. So I got to here, and then I was able to read off the analyticity properties of these functions. That was the end of the story. None of this came into that story. Okay, so the bottom line is my conclusion. Why are we able to successfully apply the mathematical techniques of analytic continuation QFT? Well, I think actually the story is similar in both the non-perturbative and the perturbative contexts. And in both cases, I think mathematical trick is the way to go. So mathematical trick is the explanation that what we have is a mere change of variables that reposes our original mathematical problem in a form that makes it mathematically more tractable. We're avoiding the singularities that are causing us problems, and it doesn't tell us anything interesting, deep about the physics. So I think that's straightforward to see in the perturbative case. The story is more complicated once you get to thinking about non-perturbative QFT. There's a more complicated argument to try and put it in the very short form as possible. Thinking about the Strokey quote. The physical structure of quantum field theory does guarantee the analyticity of the Whiteman functions, but this is not an explanation that appeals to encoding the physical structure of QFT in the Schwinger functions. It doesn't involve saying actually really anything at all about what the structure of the Schwinger functions is. There is a closely related project which involves reconstructing the quantum field theory, and in order to make that project succeed, you do need to take care to make sure that you've encoded, you've sort of mapped the physical structure that you want to capture by doing the construction. In the end, so the physical structure of the QFT has to be encoded in the Euclidean field theory, but that is going to explain the success of the construction project and not the success of the analytic continuation move. All right, and that is the end.
Questions? Raise your hands high until I acknowledge you. Sebastian?
Thanks for your talk. I have a question about I guess the last thing you said, or one of the last things you said. You said this doesn't tell us anything about the physics, right? And it's more like it's a mathematical trick. But I was wondering.
Doesn't tell us anything interesting about the physics.
Okay, interesting about the physics. But I was going to. I was wondering. One thing is why these two structures. Why we use these structures to represent the world, and then you can find formal equivalence, the formal relation between the two structures. But from the fact that you can just use formal arguments to go from one to the other one, I don't think necessarily follows that there is nothing interesting going on in the physics side, right? Because we are using these structures to model what's going on, like physically in the first place. So indirectly, it tells us a lot about the physics. I don't know if you understand it the way I'm pushing.
Yeah, so maybe this is an opportunity to say something more about this. Insofar as what I covered in this talk. So this is the sort of most well-developed Euclidean theory that I talked about, right? Is this Osterwalder-Schrader one over here. And so if I'm understanding your question, you're asking about whether this model is being used to represent something physically interesting. So that's an interesting question. So the story I told here involves, this is actually something we just made up, right? So this is a model that we constructed with, as I presented it, the sole aim of getting back up here, right? So it doesn't represent anything physical in this context of this reconstruction strategy. The interesting thing about this, though, is that if you look at this model, if you look at this sort of Bose case where you have a scalar field, actually there are models of this type that are models of classical statistical mechanics. So this is where the story gets more interesting. I've talked about that elsewhere. I was trying to bracket that part here, but I think that is a different kind of explanatory question than the one I was posing here. So here I'm trying to stick with thinking about things from the quantum field theory side and explaining why we use this kind of mathematical technique.
No.
So I need to jog the memory banks. Questions about the kind of commutativity of this diagram here?
Could you speak up a little bit?
Sorry, I'm wondering about the commutativity of this diagram. Mm-hmm. So stop me when I say something incorrect. If you start with a Whiteman model, do the vacuum expectation functions always satisfy all the Whiteman properties? Or only under certain additional constraints?
Okay, so I'm starting up here.
Start at the top right.
I'm starting at the top.
Going down to the Whiteman properties, any Whiteman model gives me Whiteman
That's where the
properties
properties
satisfying.
came from in the
Yeah,
first place,
good.
yeah.
Okay, so then
And then
we
the
Wick
theorem is
rotate.
going the other way.
Now, when we Wick rotate, do we always automatically get something that satisfies the Osterwalder-Schroeder axioms, or again, only sometimes?
Well, so there's some question here about, so these are a sufficient set of conditions that you
I
get
think
over
it's-
here?
yeah.
Right, so then there's some like variance, and there's some questions about how exactly you pick out this right set of functions that you're gonna snare with and things like that. So it's a non-trivial contribution to figure out one set of conditions over here that works. Is that what you're asking?
Okay, so okay, great. So you might get something. Okay, good. Yeah, I'm really that's what's right. Like my secondary question is if you start from here, go down to here, Wick rotate, then go back. Is it always possible to go back, or can there be problems going backwards without going up that route? If you just
Right, so if you just
reverse Wick rotate,
right, if you did this
and then tried to go backwards immediately.
and then tried to do this immediately.
Yeah.
We can get back where you started from.
Yeah.
That's a good question. I think it might depend on a lot of details about what kind of.
That was kind of my memory, but I forgot
Yeah,
all this
that's
stuff.
yeah.
So there's a physical question in the background now, right?
Yeah.
So at the very end, you said that you're not sure that this story tells us anything interesting about the physics. It seems to be a nice mathematical trick.
Right, and so I really want to. I think it's important in my thinking about this to, like, there's two parts of this story, right? I mean, there's a part of the story that ends here, and this is actually related to the story you were telling, right? And so the part of the story that ends here is, okay, this is great. Once we have these Whiteman properties, and we know that our set of functions satisfies those, then they're really, like, we have these really strong analyticity properties, right? So then that's going to license analytic continuation moves. You could be more, I think, the semantic kind of inspired strategy of reconstructing is more ambitious than that, right? And it's the more ambitious project that then is going to be a project where you have to encode in this, whatever set of axioms you pick, and there's some, you can do it different ways, right? So whatever set of axioms you pick here is going to have to somehow be encoding important physical information about quantum field theory because you're going to reconstruct it, right?
Yeah, so the thing that I'm remembering that I thought might be a kind of potential objection to you here is that, if you look at the Whiteman axioms versus the Whiteman properties, those look very similar. Like, you can see structurally how these are encoding stuff up here and vice versa.
Yeah.
The Osterwalder-Schroeder axioms include things that are not obvious over here, like reflection positivity and time ordering stuff. And so you might think that there's sort of like hidden structure over here that becomes far more transparent by taking this mapping over to this theory that is sort of structurally isomorphic in a particular way. But there's features over here that are just more obvious than they are, even though they're already buried over there.
So you're worried about you assuming too much over here.
No, I'm not worried you're assuming too much. I'm just saying there might be some interesting physics over there. Namely, there's structure over here that I don't immediately see just from looking at the structure of the Whiteman functions. But by Wick rotating and looking at the structure of the corresponding Euclidean functions, I immediately see a kind of reflection positivity that I don't see over here, for instance.
Right, and I think that's reflection positivity is one of the questions, right? Do you really need that or not? And what's the motivation for it? And
Okay, Wayne has a finger on this particular.
That's a new question.
New question? Okay, then I've got other people confused, but I've got you. Okay, Ben.
Yeah, okay, I think my question has to do with Knowles as well, but, so I was thinking, can you go back to your conclusion slide? So at some points you said that, like, these constructions, so they get you, like, from a Euclidean field theory to a structurally equivalent quantum field theory, and I mean that's also, like, implicit in some of the things that Noel is saying. But I guess
I had structurally equivalent in scare quotes, but yes.
Yeah. Okay. Well, so I'm wondering if that's true, especially if, like, if you're not sure that the diagram commutes, how do you know that? Yeah, that you're getting something that's structurally equivalent. And then, I mean, I think that would be kind of grist for your mill, because if these things aren't actually preserving the structure of the theory as one might understand it, then it's more like it's a mathematical trick and less like it's showing us anything physical. If if the things that you would read off the structure of the Euclidean theory aren't actually present in the structure of the quantum field theory. But I don't know. I mean, do you know?
Right. So, yeah. I think structurally equivalent should be. I'm trying to capture a sort of intuition, and so part of the problem here is, I'm trying to figure out how to make this argument as plausible as I can. And I think you're right. Actually, maybe structural equivalence shouldn't be in here. It's more the encoding, right? So if you have more structure on the Euclidean field theory side, that's fine. But minimally, you need the structure that you're going to then use to reconstruct your quantum field theory, right? So you need enough of the quantum field theory structure to be encoded. But it doesn't have to. You can have other structure that doesn't correspond to anything back on the quantum field theory side. Yeah. But I think, so my main argument though is, that yes, that's a strategy we should pursue because it's a route to constructing and getting new quantum field theories that might be interesting models, right? But I don't think that tells me very much about the original question that I was posing about why analytic continuation works, because that's a kind of, that's wanting more than the sort of explanation, that what I was asking for an explanation for.
Yes, very nice. I'd like two questions. One about explanation, one kind of arguments and another one explanation with an argument. So from the point of view of a physicist working in field theory, there's something that was very suggestive to me about kind of explanation one, or wanting kind of explanation one kind of type for this. Like, for example, when thinking of thermality in quantum theory, right? We face the problem that thermality in quantum theory, what gives thermality doesn't really work in quantum theory because the partition functions are not well defined, and then Kubo, Martin, and Swinger come up with this KMS condition that we call about what is the thermal state of a quantum theory, right? And then you say, okay, if the Weidmann function happens to be analytic in a particular strip, and then happens to be complex anti-periodic. So basically, like when you have a partial tau, right? A proper time of some observer that goes and observes in a field state, and then you find that the Weidmann function along the time-like trajectory, the pullback of the Weidmann function, the time-like trajectory, happens to be complex anti-periodic with respect to the time parameters. So if you analytically continue the time parameters imaginary, right? So then if you get periodicity, then that is if a state satisfies that, then whenever Gibbs thermality is well defined, this is one-to-one to thermality and generalizes thermality to cases where Gibbs thermality is not well defined. So you see, like the fact that I allow in a Weidmann function, I allow this kind of analytical continuation to complex, so imaginary time, I get a generalization of the notion of thermality. So I always saw that as some indicative of physicals. No, there's something funny because if you think of if it's a vacuum expectation, right? The 2-point function is.
So initially you said you like number one.
Yeah, that's exactly what I mean. So sorry, number two. Is that number? Yeah, number two. I meant number two. Yes.
Oh, you like number two.
No. I like both. So let me tell you why. So
Okay.
The reason of two, the reason why.
Sorry, let me find what's like.
For the reason for two,
yeah,
that I'm saying is like because for the vacuum, a Weidmann function is a correlation function because the expectation we can normalize to zero. The vacuum expectation of things. So nice. So thermality is related to the correlation of the correlations of the state, but not the correlations of the state when I consider the Weidmann function where the Weidmann function is supposed to be, but when I consider the analytical continuation of the Weidmann function to imaginary time. So I always thought of that like the notion of thermality is a way of understanding, of investing with some physicality, the analytical continuation to imaginary time of the Weidmann function.
right.
I don't know if you have any thoughts about that. And then on the other side, though, I also know that in physics, often in many fields, in particular in quantum gravity, but also in field theory, with interaction theory and so on, many times people know how to build Euclidean theory, but they have no idea how to translate and reconstruct a quantum field theory. And there's a lot of research in physics being done about only quantum gravity, where they actually make claims about Euclidean results. And I wonder, as a philosopher of physics, what you think about that, right? As in, like, if you don't know, so if you give it only, it's a mathematical trick, so the moment that you don't know how to make the connection to a proper theory, it doesn't even make sense. So it's something that's worth investigating from the physics point of view. So I guess those are my two
Yeah, okay, good. So I didn't talk about temperature at all for the good reason that I think actually that's a really tricky question. And so maybe this relates somewhat to the question earlier, right? So the way I told the story, I was just constructing these Euclidean models as imaginary models that correspond in no way to the possible world, right? But in actual physics, things get more interesting because sometimes these models turn out to be models that you can, if you physically interpret them in the right way, turn out to be models of classical statistical mechanics. Sometimes you take, and so in that case, you would take time to position. But in other cases, you can take time to temperature. Right? And that gets really complicated to figure out what exactly you're supposed to make of the physics of that. Right? So.
But it's similar analytical continuation.
Yeah. So I think that's an important question that I want to think about more. And I think this is kind of helpful background to have these two positions on the table. And so one thing you have to be really conscious of when you're comparing these types of models is there's the sort of mathematical structures, and then you have to be conscious when you're switching the physical interpretation of them, right? So I think there's lots of cases in which we have common mathematical structures at a very abstract level that then have different physical instantiations in different parts of physics that have quite different meanings. Part number two was, so do you have to analytically continue back or not? And I think that depends on what your goals are, right? So there's a sort of instrumental flavor to my number one, which is, if you have all these singularities that are preventing you from calculating the things you want to calculate, then do the thing that do the practical mathematical coordinate transformation that gets rid of the singularities, and then you can calculate the quantities you care about. But that's a very instrumentalist interpretation of what's going on. So if you want to do quantum gravity, you probably want to go beyond thinking instrumentally about what's going on, because you really want to understand the world. So that would then, I think, lead you to want to analytically continue back or do something that's more robust than this.
So I often, when I sit in communities or people doing this kind of thing, I always ask the same question. Like, okay, you're working in EM gravity. What can you learn doing this that is guaranteed to tell you something about the real world you expect not to have, not Euclidean? Like, if you cannot map, can you translate what you learn about result in a Lorentzian signature kind of theory?
Is it math or is it physics?
That's exactly the question I'm asking you, I guess. To see what you feel. Would that be math or would that be physics?
I think it depends on more details, but I think it's probably math.
I'm going to let you off the hook on this because we have a number of people left in the queue.
Sorry.
No. We can revisit this because we have an hour for discussion. It's just after the Q&A. You in the red coats, right? I'm not gonna.
Nitika.
So this is going backward rather than forward. So a question. So the premise of the talk was that you have QFTs on one side and then many body quantum physics on the other side, and you have this Wick rotation in the middle. And I was thinking if you could quotient out the quantum theory from both sides, because you could still talk about like analytical continuation between just special relativity and classical multi-body physics. And are there analogs there that are worth thinking about with the same question in mind, and would that bring any insight?
Yeah, so I think that's that's really a perfect lead into the panel discussion, which is like what's the specially relativistic about quantum field theory, right? But so the cases that I've been looking at are cases of quantum theories qualified by the fact that sometimes, depending on how you interpret this T over here, sometimes it's space and sometimes it's classical statistical mechanics. That's what you get, for example, if you are thinking about renormalization group methods in this sort of setup. Sometimes you get quantum statistical mechanics if you're thinking more about temperature. So this is a trick that's used all over the place. And I think, yes, so one reason why it would be useful to think about cases in classical physics before you get the complications of quantum theory is to be able to answer questions about, such as what's relativistic about quantum field theory, for example. If you can trace something back to classical theories that's a special property of relativistic theories, then that would be an indication that you have found something that's a special property of relativistic property.
Okay. And you? Yeah, sorry.
I was wondering how much of those techniques still work in curved spacetime. In particular, maybe one could try to take something like de Sitter spacetime and recrotate it to a Euclidean sphere.
That's beyond my knowledge. I don't know. So this is a bit, yeah, so I don't know the answer to that question.
Okay, Wayne?
This might be a kind of naive question. Can you go back to that where you had the diagram with the Whiteman and stuff? Yeah, I guess I realize I don't really understand how this works. So you got these VV satisfying the Whiteman properties, and you've got their Lorentzian signature metrics with the time direction distinguished from the spatial directions by a sign. You do the Wick rotation, you get a Euclidean metric where this is about a Euclidean signature, so none of the directions are distinguished from any of the others. Well, how do I go back then? It seems like I've thrown away a piece, looks like a crucial piece of information. I don't know which of these variables to rotate back to turn into a time variable. But do you guys have my question?
Yeah, and so I think so I guess the first thing I'm going to say is that there's a strong pull to think about Euclidean symmetries as being the appropriate symmetries for describing space, so that these must be entirely spatial coordinates, right? And I presented it that way actually, to give you that kind of intuition. But if we're in the version of this where this doesn't represent anything, it doesn't necessarily need to be space and time. It's just, but then I think you're still going to be worried, right? Because
But then I still need to know how to turn it back into space and time. But we have to go back up.
Right. So you're looking for so
Maybe it's not a well-formed question.
yeah, I think this so this is sort of there's a mathematical construction procedure, right, which is going to hinge on this kind of move, right?
Okay, Porter?
I have a historical question. You started at the beginning you started with the 66 Semantic paper and then you did arrows to Wilson and to the constructive field theorists. Could you say a little bit more about what you have in mind by the Wilson connection?
Yeah. So he cites this paper in the Nobel lecture and in the a paper with Kogut in
Not the 66 paper. He cites semantic a fair amount, but he doesn't cite.
Oh, he doesn't cite the 66 paper?
Not the Euclidean field theory. He cited semantic.
Okay. So I know he does cite it in the Nobel Prize lecture. And then, so there's also, so the connections also go this way too, right? So there's a preprint. So the Wilson Kogut paper cites a preprint of some of this work too. So that it also comes in that way. And then this work cites the semantic work as well. So it's kind of, I guess it's sort of indirectly cited. But I'd be interested to hear if you have more insight into that.
No, because I also thought that this was an actual thing for Wilson to have looked at. He doesn't cite it anywhere in real time when he's doing the RG work. It's not in any, they archived all this stuff at Cornell. It's not in any of his notes.
Interesting.
He doesn't talk about it in any sort of retrospect. He seems not to have, he seems to have been like kind of aware it was happening, but not paying much attention to it. So I was wondering.
Interesting. Yeah, no, so I think, but mostly, so that paper I think I got, was cited I got from the Nobel Prize lecture, but there's also an interesting story about why Semantic gives up on this work, right? So it wasn't picked up right away, even in his own, so it's Journal of Mathematical Physics. He would have maybe expected it to be picked up by some of the people who are working in the constructive field theory, and it took a while before they were convinced that it was a useful thing to try and do, right? I think probably because they tried other things that seemed more obvious first and they didn't work, right, to try and construct models. So I have some references on that if you're interested in the story over here, but that's interesting. I also wonder how much at that time was people going to talks and that kind of, especially in his case, in Wilson's case, right, of people getting things firsthand rather than like reading papers.
No, it's certainly possible. But yeah, there's no like citation or no evidence of it, so that would be. I agree, it seems possible, but
Hard to say.
yeah,
Okay.
no evidence for it.
Thank you.
Additional questions? Josh?
Yeah, this is a rather speculative question. I'm wondering how much you think the story you tell about analytic continuation being a mathematical trick extends to other applications of analytic continuation in science. Do you think this is like typically the case when it comes to this kind of complex analysis, or do you think there's at least plausibly some instances in applied mathematics where there is a real physical explanation to be told?
So again, I think it's important to be clear about what you're trying to explain, right? So if you're just trying to explain conditions under which you can legitimately analytically continue, then you're going to be looking for the analyticity properties, right? Which and then it might be at a case-specific base. There might be theories in which that's going to encode important physical information. I don't know. I think not in this case. There's also the sort of instrumental flavor to the explanation that I'm giving as well, right? So it's going to depend on what your goals are in applying the technique. If it's to get rid of singularities that are preventing you from calculating some quantity, then that seems like a case in which you might tend more towards accepting the mathematical trick kind of explanation. I think the short answer is it's going to depend on the context.
Okay, I'm going to abuse my privilege as chair and just add one note on a finger on Josh's question. So here's a story I've heard told in a certain big pink book that you may or may not be familiar with about what's going on in cases like this, which is applies to the more general cases that Josh may have in mind. But I think, at least on its face, seems like the kind of story one might tell here, which is what happens when we analytically continue is that what were these messy dynamical hyperbolic field equations become elliptic, and now things are smoothed out. And like we're considering the period after all the messy dynamical information is shaken out and convert to more like a boundary problem. To me, that sounds like a physical story specifically about why analytic continuation is giving us the kind of information that it's giving us in the Euclidean case. Is that
well?
Does
So
that not
this
apply here, or is that story wrong?
So yes, I think that the story sort of does apply, but then there's another part of the pink book which is about spilling milk, right, or spilling beer or whatever your beverage is, and then that part focuses more on the question of whether it's legitimate to assume that you can use analytical functions to describe the whatever pattern of spilled milk or spilled beer or something like that, right? And so I think that actually might be a strand that I need to think about more in this context, because what happens after you prove that you have these, the reconstruction theorem, and you have the Whiteman functions with these very strong, relative to the algebraic QFT context, in particular analyticity properties? Well, then the Riche-Leader theorem falls out of that, right? So then that's a point at which you might be worried about whether you've assumed too much about what kinds of functions are the right kinds of functions to describe correlations, right? So I think that part of the story might tie into a Wilsonian kind of theory story.
Okay, please join me in thanking Doreen again.